First up on this paper, we've got the electromagnetic spectrum or electromagnetic waves, and the first task is to fill in the missing blanks. So we've got A, B and C up here that are missing. Now if you've learnt your EM spectrum in order, we should know that it goes radio, microwave, infrared, visible, UV, X-rays and gamma rays. So therefore A is radio, B is microwaves, and C are X-rays. Okay, right, next one, we are looking for some similarities and difference between ultraviolet and gamma rays. Okay, now in my opinion the difference is slightly easier here to know, because again if you've revised your EM spectrum you will know that all the waves have different wavelengths and frequencies. So either one of those would be absolutely fine. You have to say which one has the higher wavelength or frequency. So here I'm just going to say gamma has a higher frequency. Now the similarities between electromagnetic spectrum waves, all of these have these in common, not just ultraviolet and gamma rays, but you could say they're all transverse. You could say they all have the same speed, like you don't need to say multiple of these, just one of these is fine, same speed, etc, etc. Okay, they travel through a vacuum, that kind of thing. All right, other options for differences, you could talk about lower wavelength for gamma, you could talk about it has a higher ionization or is more likely to ionize, that kind of thing as well. Onto the right hand side, we're talking about white light being split into colours. It says it changes direction as it enters the glass prism. As you can see up here, it kind of changes, goes a bit shallower angle. Now, the name that's given to that process is refraction, not reflection, refraction. Over the page, let's continue with question 1. So question 1, we've got an equation question, our first one of the paper so far. The equation that links frequency, wavelength and wave speed is speed equals frequency times wavelength. You can do symbol forms or in words, it doesn't really matter here. And we're going to use our FIFA method of calculations to make sure we are getting full marks. So if you don't know, FIFA stands for formula. So formula or equation, which is speed equals frequency times wavelength. We're going to insert our values, then fine tune and get an answer. I don't like triangles, I don't like rearranging before you've got your values in, because you get a mark for doing this next bit. Okay, so we don't know what frequency is, so I'm going to leave that as a blank. You can leave it as an X if you want to. We do know what wavelength is, it tells us that at the start of the question. Okay, and that's your first mark secured. Next, we've got to figure out what to do. I've currently got f, the thing I'm trying to find, multiplied by 5 times 10 to the power minus 7. So I need to get rid of that. So to get rid of it from this side, I need to divide both sides by it, and that will then give us the sum to find my final answer. So to find the frequency, it's 3 times 10 to the power 8 divided by 5 times 10 to the power minus 7. And you stick that in your calculator, making sure you're being really careful of brackets, and that will equal 6 times 10 to the power 14. Okay, please make sure you've got a calculator that allows you to do standard form and scientific calculator, otherwise that question's a bit of a nightmare without it. So for that first question, I think generally speaking and difficulty levels, I'd say that's a fairly medium sort of calculation. There's a bit of standard form to make it slightly tricky. I'd say this whole side of the page though should be relatively straightforward. If you revise the electromagnetic spectrum, a couple of marks or 1 mark for each thing, it's not too bad start to a higher tier paper. Next we get on to some of the trickier stuff, because we've got to require a practical for question 2, which is talking about the acceleration of a trolley. And you might notice this diagram looks pretty blank. That's deliberate because it says the diagram shows some of the equipment used, and you're going to describe a method using any extra equipment. So this is one of the harder required practicals you could get for paper 2. So what I'm going to do is fill in the extra equipment you need on the diagram, then we'll start writing down our method. Okay, now the first thing, this car could run down the runway quite easily. However, we need to be able to vary the force acting on it. So with any version of this practical, there's a piece of string that gets attached to a pulley which is clamped to the end of the table. So I'm just going to label those things on. You don't need to be that detailed with your diagram at all. I'm just making sure you guys can kind of picture what's going on. Now the string will go past the pulley, which is like a kind of in a circle shape. It'll go down here and you'll have a mass hanger with masses hanging off the end. Okay. So one more piece of equipment, which we're going to describe later on in the method, but that's the general setup. Okay, so you add masses here, you let the trolley go, the trolley will run this way. Now for this practical, what we need to be able to investigate, as the question suggests, is how the acceleration of the trolley is affected by the force. Okay. Now the force is produced by, well, the force we're measuring, we can change by adding masses to this end of the pulley. The acceleration is the tricky thing to be able to measure. Okay, so we'll talk about that in a second. So let's just get our first couple of bullet points down for our method. Now we're going to mention the extra equipment that's not used, so we don't need to mention about the slope or the table or the runway because it's already in the diagram, so you don't get marks for that. So we'd say something like clamp a pulley. Okay, so that's this thing here to the end of the desk and attach string to the car, and then we're going to attach the other end of the string to a mass hanger. And we're going to like drape it or kind of place the string over the pulley. Okay, so this is an example of a required practical method, which this won't be exactly what you've written down in your books. However, they've given us an incomplete diagram, so we get extra marks for saying things like that, for kind of filling in the missing pieces. Okay, so what we're going to do is we're going to essentially talk about now how to measure the acceleration. Okay, so measure acceleration and then changing the force. So we'll do that second. Now there's a few different ways of doing this. This is just the way my school does it. I think one of the easier ways to mention in the exam. Okay, so to measure acceleration, essentially what we're going to do is use this equation here. So acceleration is change in velocity divided by time. Now time is very easy to measure. That's using a stopwatch or stop clock. Change in velocity is a bit trickier. Okay, so to measure the change in velocity, what we're going to need to do is use something called a light gate. Okay, so you have it clamped in place here. You don't need to draw it on your diagram necessarily for this question, but just to kind of help you visualize it a little bit. Okay, these light gates can measure a few different things. There are electronic sensors that can measure. In our case, we're going to use it to measure the speed when it passes one point, and then the speed when it passes the other point, and then we can find the change in speed or change in velocity here. Light gates can also measure acceleration. They can also measure time. However, I'm going to keep those two things separate just so we can talk about combining them later in our equation. Okay. So, like I said, there's a few different ways you could do it. You could measure distance. We're not going to worry about this for now. Okay. So that's what the setup is. Let's start writing our method for the main part of the practical. So we're going to release the car from the top of the runway, and we're going to use a stop clock to measure time taken to travel between 2 points. Okay, now those 2 points we don't need to write on here, but they're there and there. So the next statement we're going to say we're going to use light gates to measure the change in velocity between those two same points. Okay, and now to find the acceleration, that's the easy bit. We're just going to say find acceleration using our equation. I'm just going to say acceleration equals change in velocity divided by time. So that's our extra equipment to the diagram. That's how we measure acceleration. And the last thing we're going to say is how we vary the force. Now again, there's a couple of ways of doing this. You could alter the height of the runway. However, we're going to talk about the masses here. So we're going to say add another mass to the hanger and repeat. Okay, so you might repeat numbered stages or repeat those steps as you've written it there. Okay, now mass isn't the same thing as weight, so you could even put a bit extra detail in here and say weight equals the mass you've added times by g, or 9.81 for each thing. Okay, now we could talk about further masses. However, there's no table of results, so we don't need to know specifically what they are, but the idea of adding more masses, you could say more masses to the hanger would be sufficient here. That's our required practical question. Okay, on to the rest of question 2, and we've got one set of results here. It says, which of Newton's laws, by the way there are 3, predict the acceleration of the trolley is proportional to the resultant force. You do just need to know these. Okay, Newton's second law is the one that says F equals m times a, or acceleration is proportional to force on the trolley. Next, we're going to work out, we're going to use that equation. Okay, so we are going to try and work out the acceleration of the trolley when the resultant force is 3.6. But we don't need to use the full equation here because it tells us in the table that for 1.2 newtons the acceleration is 1.6. So for 3.6 newtons, if it's 1.2 and now it's 3.6, that's an increase of times by 3. It's gone up by a factor of 3. So essentially what we then do is we say, okay, well 3.6 over 1.2, it means it's gone up 3. Okay, so times by 3 for the force, so therefore we know they're proportional, told us that earlier, so therefore the acceleration is going to be 1.6 times by 3, which if you stick it in your calculator is 4.8 meters per second squared. Another question up this side. This time we are going to use the equation with F equals m times a. So let's just jot that down. You could do it in words or symbols. And we're going to work out the mass of the trolley. Okay, so let's make sure we've got our FIFA all up and loaded to use. So F equals m times a. The acceleration of the trolley is 1.2. The mass we don't know, and the force is 0.42. So let's write those in. Mass we don't know, write an x or leave it as m. Okay, that's our first mark already. Next we're going to do how to get rid of a times by 1.2. Well, we have to then divide by 1.2. So therefore my mass is going to equal 0.42 divided by 1.2. If you stick that into your calculator, you should find that the mass equals 0.35. Okay, now don't do what some people do, which is do the smaller one divide by big one divide by the smaller one. It doesn't always work out like that. You've got to just use the FIFA method or something similar to be able to get your marks here. Okay, so I'd say for this page in general, I'd say it's potentially easy to medium. I think a couple of equation type questions and multiple choice. I would say this is a hard required practical, and the fact they don't give you all the equipment is a bit sneaky. So that'd be one. You're trying to make sure you are reading the question carefully and you revise your required practicals really as much as you can. Now, this question is also kind of related to required practical, is a ripple tank that we're going to use to demonstrate water waves. The teacher used a lamp to project the shadow of the water waves on a screen, and it says, you've got the figure there, the picture, 1 millimeter on figure 4 represents 5 millimeters on the screen. Determine an accurate value for the wavelength of the waves on the screen. Now, to be able to know this, we need to try and ditch the model of waves being like this, okay, which is one wave representing waves, and use the idea of wave fronts, okay. So for wave fronts, then you will need to measure the wavelength will be the distance between one line to another. However, there is an issue with measuring the distance from one line to another, being that it's quite a small distance, and to use a ruler to do so, actually, you know, it's a quite high chance of error, because you could measure from the left-hand side of one, the right-hand side of another. It's only about a centimetre or so, so it's not the most accurate way of doing it. So what we do instead, and usually the clues in the fact that it's accurate, is that we are going to measure across multiple lines. Okay, now the highest number we can measure across is 1, 2, 3, 4, 5, 6, 7, 8 of them. So we're going to measure across all 8. Okay, so grab your ruler. I'm going to say from the centre of the first one to that one there, we've got, my ruler's doing it in millimetres, but I'd say that's 11.4 meters. So 11.4 centimetres, beg your pardon. So 8 wavelengths. Actually, I keep it in millimeters because that's what the answer wants it to. So 8 millimeters, 113 millimeters for 8 wavelengths. Okay. Then this is the sneaky bit. It says 1 millimeter here represents 5 millimeters on the screen. So times by 5 to get what the actual distance was. And then what we have to do is divide by 8 to find out what that is overall. So times by 5 is 565 millimeters. Then we get 8 wavelengths, so 1 wavelength is, you divide by 8 because I measured across 8, and that is about 70.6. And there's a bit of a range for this question. Anything between 68 and 72 is absolutely fine. Okay, more practical skills in this question. We are trying to work out we've got the mean worked out for us, so we're trying to work out a value that will help us find the mean. So the mean, we should know, is all the values added together, divide by 5, because there's 5 different measurements. Now how the best way to set out the solution is, rather than trial and error and getting the right answer, is by doing something like this. So you'd say 96, 99, all the values added together, plus x, because I don't know what that is, plus 97, divide by, there are 5 values, it gives you 97. And then essentially you solve for x, okay, so x is what we're trying to find there, so it'd be 97 times 5 gives you x plus all these numbers, so you subtract each one in turn, and you should find that the x is going to be 96 millimeters. Now, the last one is about knowing what precise means, okay? So the thing people often forget to revise in practical skills is the difference between accuracy and precision. So my analogy is, let's say you have a dartboard, someone's aiming for the bullseye, they're not getting it every time, however, their results are all very close around the same point. This would be an example of something being precise, okay? So it's not close to the true value, that would be what accuracy means. So if something's accurate, it's close to a true value, but the idea is the spread about the mean is very small, so all the results are essentially very close together. So it would actually be the second box there. Okay, finishing off question 3, the difference between transverse and longitudinal wave. This is one of those you just need to know perfectly, okay? So we can start off with either one, and you can't, there's no shortcuts in this, you just have to say it, have to basically say it exactly as I'm saying it. So you'd say transverse waves, the oscillations, you could say vibrations here, are perpendicular, or at 90 degrees, to direction of the energy transfer of the wave, or the wave direction. Energy transfers are things that's in mark schemes though, so I've memorized that. Whereas longitudinal is basically the same definition, apart from this means the oscillations, instead of being perpendicular, are parallel or in the same direction to the direction of energy transfer. Okay, just to give you a bit of indication of what that means. So transverse, something's causing it by going up and down. The wave is going at right angles to the wave, or perpendicular, whereas longitudinal waves, the oscillations are going in the same direction as the wave. Okay, so there's a bit of bonus information there. That's how sound waves work. This is how light waves or other EM waves work, because they are transverse. Now for this question, I think this is a bit of an unusual question, the practical. I think that it's a tricky definition to remember, but it comes up a lot, so revise it. This is all a bit unusual, okay, to get the mean given to you, but try and work out one of the answers, and this is a genuinely question I haven't seen something quite like this before. However, this is one of those like, hey, what am I going to be asked to find out? What practical do I know about this? How can I figure this out? Underline everything in the question, and you should be fine. But it's a little bit of an unusual question, that part of question 3. Okay, on to question 4, and we've got a question all about magnetic fields. So before we move on to magnetic fields question, this is a example of essentially motor effect. We'll come on to that later. It says the rod remains stationary when the switch is open. The tendency, or like kind of the probability of an object to remain stationary, it's called inertia. Okay, it's a good phrase to learn. That's a good definition to learn. Inertia, the tendency for an object to remain stationary instead of moving or accelerating. Now for the next one, it's our friend Fleming's left-hand rule. You might remember learning this in lesson, so it's going to be hard to show on a visualizer, but you've got to get your left hand out. For this diagram here, your thumb is the direction the rod will go in, so that's what we need to find out, because the direction the rod will accelerate in, that's our motion. Field is our first finger, that goes from north to south, so we need to point that in the downwards direction. Second finger is current, so which way is the current going? Now we can figure that out because it's conventional current. It's from positive to negative, so it's going this way, and it's kind of going this way across the rod and then down this way. Okay, so you've kind of got to like twist your arm a little bit, which is quite hard for me to do, so that you've got something that looks a bit like this. Okay, and if you do that properly, your thumb should point out, once you've twisted your wrist a little bit, to the right hand side, so it goes to the right. Much more likely, though, it's usually only going to be one mark, that kind of question, is how you could increase the acceleration or increase the force of the copper rod. Okay, this question comes up a lot. So what we'd do, we'd increase the current, or we could increase the magnetic field strength, but it says only use one and explain one, so increase the current so that the force or the resultant force increases. Okay, so notice you don't get 2 marks for saying 2 things here, because it says one, but it does ask you to explain it. So you've got to say how that bit works in this question. Okay, over to the next bit of question 4. This time we've got some permanent magnets, and the question says, the question tells us there's an iron bar and a permanent magnet. It says describe how the permanent magnet could be used to test if the iron bar is also a permanent magnet or not. Okay, Now we should know, to be able to understand this question, we need to know, well, how do iron bars behave next to a permanent magnet? So iron is magnetic, okay, meaning it can become a magnet, but it's only ever attracted to magnets. Okay, you cannot repel iron. It's a magnetic material but not a magnet, so it becomes attracted, not repelled. Okay, so with that knowledge in hand, what we do is we bring the iron bar close to one end. So let's say the north end, I'm going to say N end, okay? Then we'd see if it attracts or repels, essentially, okay? Now, if it attracts, then we know it could be an iron magnet. Sorry, if it attracts, we know it could be either, and if it repels, we know it's definitely not an iron bar. So north end and south end, if it attracts to both, it is an iron bar. If it repels, it is a permanent magnet. So I'm going to run out of room here. Don't ever do this in real thing. Don't actually write on the other side of the box, outside the box. Not a good thing to do. Okay. Cool. All right, on to the next one. We talk about compasses. The question shows you a plotting compass like you use on Duke of Edinburgh or something like that. It says explain how a magnetic compass provides evidence the Earth has a magnetic field. Okay. Now, inside a compass, the reason why it moves depending on where you are, points towards north, is because there is essentially a tiny little magnet inside the compass needle. So what we'd say is that the compass or the compass needle always points north, always points in the same direction, okay, and that's because it aligns itself with the Earth's magnetic field. So you could say things like it kind of follows the shape of the Earth's magnetic field, things like that, but align's a really good word to use. Now the idea is, if you didn't know, the Earth has essentially a giant magnet inside it. It doesn't really, has lots of molten iron, but has a magnetic field, okay, and compasses will always point towards north. But fun fact, however, compasses will point actually towards a magnetic south pole in the Earth's core, which is actually at the North Pole, which I know is very confusing. That's what bit of context for this question. Okay, so that's question 3 done. I'd say overall it's probably a medium for this page. I'd say if you are keeping your wits about you, you can kind of explain that one quite straightforwardly. Fleming's left-hand rule is kind of tricky. However, it's only 1 mark for that bit. This is the bit you should be nailing 2 marks on, really, for the kind of explaining question for 4.3. Right, moving on to question 5. We got one of these cool garden chairs hanging from outside, and it asked us to describe the relationship between weight and extension. Now we need to know what these symbols mean, okay? It's one of those things, it is on your specification. We should know this means less than, this is obviously equal to, this means proportional, and the little squiggly lines means essentially like approximate, so approximated to that, okay? Now, how do you be able to find this one out? Well, there's an equation for force and extension, of which weight is a force. Okay, so therefore you know this is constant. So force is proportional to extension. Therefore, weight is proportional to extension. And we're actually going to use that equation in 5.2. It gives us a weight, which again essentially is a force, and gives us an extension. And we are asked to find the spring constant. So what we do is we find the correct equation. Force equals K, spring constant, times by extension. I'm going to plug my values in just like normal. So insert values, fine tune, then give an answer. So the value we're going to use for force is 750. K I don't know, so I could leave it as an X or a K, whatever I want to do. And before we dive in, we should notice this is in millimeters. So d millimeters, to get into meters, is divide by 1,000, or 10 to the power 3, so 0.060 meters. Okay, so 0.060 goes here. That's 2 marks secured already. Next, to find what K is itself, we need to get rid of our times by 0.06, so we divide both sides by 0.06 to get the K by itself. And if you put that into your calculator and you work it out properly, you should find that equals 12,500 newtons per meter. On to the next part of question 5, a definition for us here about inelastically deformed. So the idea is if something's elastic or elastically deformed, it goes back to its original shape. So inelastic means a material will not go back to its original length when any force has been applied. Sorry, been removed. Beg pardon. Okay, so an object won't return to its original, you could say shape here, or original, but I would say length, much easier. I like to come up with mark schemes. Original length when force is removed. So those are your 2 marks for that question. Next we've got another equation involving a physics equation sheet, and we've got to use the information up here. Sometimes the information isn't just in the first bit of the question, it's near the top as well. So this time we've got energy and we've got a spring constant. It's a new spring we're talking about here. We're trying to find extension. So the correct equation to use here is that energy, elastic potential energy, equals half times by spring constant times by extension squared. So we're trying to find extension, so let's again put our values in, so make sure we are keeping track of our numbers. So elastic potential energy 1800, half is a half, spring constant is 225, and the extension we do not know what it is, so I'm just going to leave it as e squared for the time being. Now you can do this bit first if you want to, a half times by 225. I've not really got room to do so here, but I can just transfer both those things. They're currently times by e squared, so I need to divide them from this side to be able to find e squared by itself. Just make sure you're keeping an eye on brackets and things like that. And what you'll find is that that equals e, between brackets there, that equals e squared. Okay, so to find e, the extension overall, you'll therefore need to do the square root of these things. So you might want to do this little sum first. So doing that part first, you'll find that e squared, if you put that into your calculator, equals 16. So therefore e is the square root of it, so it equals 4 meters. No unit conversions needed there. So please make sure you copy that from the equation sheet, you're carrying it through the squared symbol, otherwise you're going to forget to square root it at the end. Now we've got a new one, loads of calculations about springs in this question. It says evaluate, that's an interesting command word. Evaluate means kind of weigh up, like compare, is it suitable or not. The suitability of a new spring to hang the chair. Gives us the potential energy again, gives us a spring constant again, but this time we've got the weight of the person included, and this information is new here. It tells us the distance between the bottom of the chair and the ground is 30 centimeters. So if we look back to the chair itself, essentially what they're saying is this is 30 centimeters. If it extends by bigger than that, then we're going to be in trouble. It's not going to be suitable to use for the chair. So what we're going to try and work out is the extension for this situation here. So with this person being used, I'm going to do F equals K times E. F is the force or the weight of the person, so 750 newtons. K we know, the extension we don't know, so let's find that out. So the extension we should be able to do is 750 divided by 225, which equals 3.3, etc. Meters. Okay, now that should ring alarm bells in our head because this is in centimeters, this is 0.30 meters. Now obviously 3.3 meters is quite a bit bigger than 0.3 meters. Okay, so we've got 2 marks already just for that calculation. Then, because it's an evaluate question, not just a calculate question, you've then got to say, well actually the extension will be too big or too great, so the spring is not suitable. Okay, now you don't get any marks in this question just for saying yes it is suitable, no it's not. You've got to back it up with a calculation, but that's the kind of concluding statement you'd say for a question like that. So let's evaluate the difficulty of these then. So I'd say this potentially is a medium type of calculation because we've got a conversion to do and a little bit of rearranging. This one probably medium as well, and definition you need to know deformed. I'd say this one's hard. I think this, generally speaking, the way it's phrased in terms of evaluate is kind of tricky, but if a question says include a calculation, just do the calculation bit and you might find it makes more sense. And also this question had 2 marks for the calculation regardless of anything else, which is quite nice. Right, on to question 6. We've got another calculation. Lots of these come up in combined science higher tier. Let's start underlining. So the situation is a child dropping a stone. It says it passes the child's feet with a velocity of 3.1. The child's feet are 6.3 meters above the water, so that's the distance. We've got acceleration due to gravity, and it says calculate the velocity of stone as it hits the water. Now, as it's travelling down, as it hits the water, that is the final velocity. So we use the symbol V for that. As it's passing the child's foot, we say that's U, so that's the initial velocity. Okay, so initial velocity, because this is going to be important to not mix those two up when we do an equation in a second. Now, the equation that can help us is going to be this one here. It's got to have acceleration, distance, final, and initial velocity. It's going to be this beautiful one with all the squares and horrible stuff in it. That I'm sure you guys enjoy. So first stage is just going to be plugging our values in. Okay, so we don't know what the final velocity is. That's what we're trying to find out as it hits the water. Initial velocity we said is 3.1. We're going to make sure we square it. On the right hand side, 2 times the acceleration, 9.8, times by the distance, which is 6.3. Now you might find, to make your life easy, you might want to do this sum first. I'm going to do that first just to make life a bit easier later, make it simpler to figure out what's going on. And that happens to equal 123.48. Now on the left hand side I've stayed the same so far. I need to find what the final velocity is by itself. So how do I get rid of a minus 3.1 squared? I've got to do the opposite. So onto the right hand side it goes. So 123.48. Get rid of the the minus 3.1 squared by plussing it onto this side. And now you can actually square it and find out what this sum equals overall. And that equals 133.9. I'm going to the right hand side because I've not got room down here. Okay, that's not the end of the story yet because that's what v squared is. Okay, so just to go on here, so v therefore equals the square root of 133.9, which equals, if you put into your calculator, about 11.5, etc. But final mark, it says in 2 significant figures. Okay, it even says it on the answer line as well. So therefore that's going to be 2 significant figures. We round up, so it's 12 to 12 meters per second, and that's to 2 significant figures. That's where your final mark is from in this question. Now, over the page it says, moving away from the maths, velocity is a vector. Describe the velocity of the stone as it falls through the air. Note it's a describe question, not an explain question. So the velocity is made up of speed and direction, basically. So speed with a direction. So we need to talk about both those things. It even gives us a clue there by saying it's a vector. So let's then mention what happens to the speed. As it goes through, we should know it accelerates or speed increases. So we could say the magnitude or the velocity increases. Could say magnitude here, but we talk about the direction. Okay, we could say the direction is constant or doesn't change. Okay, it's a bit of a sneaky on that. A lot of people would say the velocity increases and try and explain why. However, the fact it says it's a vector is hinting we should know we need to talk about direction as well in this question. 6.3 is a really typical terminal velocity question. Okay, now how do we know it's a terminal velocity question? Well, it talks about something moving through water or air, and it talks about a constant velocity. It doesn't have to mention the fact that it's terminal velocity for you to figure that out. Okay, so for us to be able to work out what to say then, we need to know what the forces are that are acting, and then just dive into describing them. Okay, so it says the velocity is going this way. Let's label the forces. Now we should know that weight goes downwards. You could say gravity at GCSE, even though technically gravity is not a force. Now in water, we don't say it's air resistance. We could say water resistance. Drag is absolutely fine to say here. Those are the forces that are acting. Okay, and it's a big explain question. It's 4 marks, so we can use bullet points to explain why it goes to a constant velocity. Okay, so I'm going to do a couple of diagrams here just to show you initially. So there's the stone. So initially, weight is going to be bigger than drag. So essentially, it will accelerate. Okay, so we're going to talk about why it slows. Oh, beg your pardon. Sorry. The question only asks. I've just noticed now. The question says why does it slow to a constant velocity? Okay, so actually, we don't need to talk about anything else. So actually, it's a little bit untypical of terminal velocity questions because often they'll ask you to talk about why it accelerates and comes to a constant, but it only says why it slows to a constant velocity. So in this case, I'm going to have to change my mind a little bit and say, well, actually, for it to slow down, the drag force must be bigger than the weight for it to slow down. Otherwise, it will keep accelerating or go at a constant speed. So drag is force, or water resistance is larger than the weight. And that then causes, and this is such a good word to say in any force questions, is to talk about what happens to the force. It's a resultant force. Okay, so we say there is a resultant force, and you can say acting upwards. we could say opposite to the direction the stone is falling in. So therefore we know it's going to slow it down. However, it doesn't stop, okay, so it keeps on moving, and the reason for that is because drag will decrease as it slows down, basically as velocity decreases, okay, until drag is equal to sorry, I can't spell drag. Drag is equal to weight, so velocity is constant. Okay, so even I got caught out a little bit by that then, I forgot my marking this, but make sure if it says about it's just slowing, you just talk about it slowing. However, if it was asking about it accelerating or explaining a graph, normally at the start the weight is going to be bigger than drag. However, this case it just talks about how it slows down. So for that reason, I feel like I've got to give that question a hard one, really, to remember. But I'd say I go medium/hard because I do think if you keep your wits about you towards the end of a paper, you'll be able to remember that one better. I'd say this is a fairly tricky calculation because I think that's one of the harder equations to use and rearranging, whereas this one I think should be a little bit easier because you've just got to keep your eye on the question. It talks about vectors having a magnitude and a direction. Okay, for our last question on this paper, we've got a velocity time graph. It says the car contains a device called a black box. It records velocity and acceleration, and this is the graph that shows how its velocity changes. So the first step is to work out the deceleration of the car. Now we should know the deceleration of the car, we are only talking about this section here, because that's the only time where it's slowing down or decelerating. So at that point then, what we need to then look at is, well, what is deceleration? There's no equation with that in, but we should know that this is basically negative acceleration. Okay, so we can use the same equations we'd normally use for acceleration. The one I'm thinking of here is change in velocity divided by time. So let's use our graph. There are 5 boxes between 25 and 30. Therefore, this one is 1 box in, is 26. And this goes, the time goes from 2 to basically halfway between these 2 boxes. So this is 5.25 here. Okay, so 2 to 5.25, and the velocity, it goes all the way from 26 to 0. So the change will be from, like I said, 5.25 minus 2, not the whole thing, just that section there. So if you're able to work that bit out, then you should find it ends up being 8, and we need the unit for this one, so it's meters per second squared is the unit for acceleration. Okay, please make sure you're reading that graph correctly though, okay, because that's not quite 5.2, it's not quite 5.3, it's halfway in between. Next, onto the right hand side, we've got a 5 marker. Now normally this indicates multi-step, which this one kind of is. This paper doesn't really have a multi-step equation per se as we look at it, because this one we can just use the graph, but it kind of is a multi-step equation because there's multiple things to do. There's a couple of different ways to go about doing it as well. It said the driver has a reaction time of 0.75 seconds. Determine the stopping distance of the car. Okay, so we should know stopping distance is essentially made up of thinking plus braking. That will help us out, because the information they've given us there is only related to the thinking distance overall. So a thinking distance is the easier part, because that is this section here. I'm just going to kind of label it on the diagram. Thinking distance is this first box here. Okay. Now what we need to know for this is the equation speed equals distance times time. Now the much better way of doing it, in my opinion, is to be able to just use the area of the graph in general. Okay, but we're going to work out, so the thinking first of all. Okay, so the area of the velocity time graph is equal to the distance travelled. Okay, so the area of this section here is just a rectangle, so therefore the area is 26, that's how tall it is, times by 2 seconds, which is how, which is how the time we've got is 0.75, not 2, ignore me, so 0.75, and therefore that would equal, if you times those two things together, 19.5 meters. So I should just correct that bit from the graph there. So because it's 0.75, the reaction time essentially is not the whole section in orange. Okay, we will just be looking at this part here. Okay, however, for that question, it's probably easiest just to do distance equals velocity times time for that part of the question, because if you use the whole time, that's not the whole reaction time. He's traveling at constant speed there, then he spots the hazard, and that period there, 0.75 seconds, is how long it takes him to react to the hazard. Now the area of the second bit, so the braking distance, you definitely do use the area of the graph. I think that's by far easier. So we're going to use this, find the area of this section here, which is a triangle. So therefore, the area of a triangle equals half times base times height. So we're going to do half times by the base. Now the reason this is, I think, better because we've already worked out these values previously. Okay, so this is between 2 and 5.25. So 5.25 minus 2, and the height we already said is 26. Okay, so if you stick those values in for this part of the equation, you should find that's 42.25. Okay, so that's your braking, that's your braking, that's your thinking distance. For the total stopping distance, we essentially need to add these values together. So 19.5 and 42.25 meters. So if you stick them in your calculator together, the total answer is 61.75. Now while we're here, an alternative way of working out the braking distance is by cracking out this equation again, the v squared minus u squared equals 2as equation. You definitely can use that if you want to, because we've already got the acceleration value. However, I think this one is far easier just to find the area of a triangle rather than use that complicated looking equation again. Now 7.3 is all about what can happen if large decelerations occur and why they might be dangerous. Okay, so there's a couple of things we could say for this question. My top one would just be to say, well, use an equation in these types of questions and say, well, I know decelerations are negative accelerations, so we'd say something like the greater the deceleration, the higher or the greater the force. Okay, then you'd say, well, large forces or high forces can cause injury. So there are a couple of other ways you could say it in the mark scheme. You could say about heating. So essentially, you'd say brakes. I should write it up here. So brakes can overheat, etc., not work properly. However, I think that's by far the best kind of the best answer for this question, I would say. So that's question 7. I'd say, generally speaking, because it's a kind of tricky maths equation, I'd say it's potentially a hard one. I think these two are relatively straightforward, so maybe medium overall. And that's the end of the Combined Science higher tier paper. Sorry the lighting's been a bit weird throughout. I'll try and look into that for the next one I do. Anyway, I hope you found that useful. And just a reminder, this was 2023 higher tier Combined Science.